everybody, Harold here. Part 3 in the secure password hashing series. We're going to move to the next most secure level, Scrypt. Scrypt is a key derivation function. You'll see KDF for password hashing. Turns it into a crypto key using random salt, which is, if you've seen my first two videos, extra digits appended or prepended in case everybody's password is password 123. They don't hash the same. CPU and memory intensive, so it costs more, but you can adjust the parameters to balance your speed and security. It's ideal for storing passwords, deriving encryption keys, proving identity. They use it in the blockchain. Here's our SHA-256 from hashlib, but a lot of these guys. Here's the SHA-256 from hashlib, but if you can see down here, Litecoin and Dogecoin use script, Scrypt. Uh, Basic usage, it is a part of hashlib. I didn't show it to you with hashlib because it's kind of different. So we want to use this. We want to import hashlib and OS. Uh, like I said, hashlib algorithms available won't show script. You have to know it's there pretty much. To declare a password and salt it. My super secret password 123, and we make some salt. OSU random 16 is equivalent to secrets token not hacked. Cryptographically secure alternative. I just wanted to show you another way you could generate a secret token. You'll see it in a lot of code. Create an encrypted key. The key equals hashlib.scrypt. Let me read this through and then we'll explain it. So key equals hashlib.scrypt. Password. Salt is salt. I don't know why I have all these spaces in here. N equals 2 to the 14th. R equals 8. P equals 1. DK equals 64. So print the salt and the derived key. And the N is the CPU memory cost factor. It's got to be a power of 2. Typically 2 to the 14th or 2 to the 20th or higher. Make it exponentially slower and more memory intensive. And this has the largest impact on how secure it is. R is the block size, usually 8. The larger, the more memory used. P is the parallelization factor. How many threads do you want to run it on? More threads, more cost. We're just going to run on one thread. DK is the length of the derived key. We're going to use a 64-bit output. So we said DK 64. So let's run this. And I forgot to run my password cell. So let's run this again. The salt is this. The derived key is this. Look at that string. How hard would that be to break? So we're getting more and more harder to break, but it's costing us more CPU. Default settings like 2 to the 14th, R8 for the block size, 1 thread, and DK 64. Secure and practical for most desktop server applications. You want to get really hardcore, then ramp those up. Verify the password. You store the salt and the hash key and rehash the password with the same salt and compare. So you would import hashlib and OS, define hash password, take the string, get some salt with OSU random, get the key with hashlib.scrypt, password encode, our rounds and our threads and our length. Verify the password, stored salt. I don't want you guys to try to follow along and type this. You can copy it out of GitHub, but just kind of follow along with me. Uh, Stored salt, stored key, and the password attempt. New key, is encoded password attempt with the stored salt. And return if new key equals stored key. So to demo it, the salt and the key equals a hash password, my super secret password 123. Print the salt and the key. If they match, match. If they don't match, don't match. So they matched when I put in the right password. They didn't match when I put in wrong pass. Why script is stronger? It's memory hard. Requires a big byte of RAM for each attempt. So if you're using attacker's using a GPU or an ASIC, it kind of slows them down. Configurable, you can change the parameters as your hardware gets faster, or their hardware, the attacker's hardware gets faster to maintain security over time. Built into Python, it's natively available in hashlib since 3.6. In short, it balances CPU and memory costs to resist traditional and specialized hardware attacks. Little tip, you can store the hash compactly. You can store a salt key together in a single string using base64. So this code's basically the same. We define the hash, store password, we define the salt. And the key, we return it in base64 encode, the salt, the key. And to verify, we take that raw and the salt and hash the new key and compare and stored, match, verify. Then we say stored equals hash and store my super secret password stored, print match, verify, stored my super secret password 123. So it stored that and it matched it. I'll put it back in. In the summary, generate salt. I used OSU random 16. You could use secrets. I hashed the password with hashlib.scrypt. Memory hard and highly secure. Verify the password. I rehashed it, compared using the same salt and the same parameters. And it stored the data in base64 encode. Combine the salt and the derived key safely for storage. Always store the salt by the hash. It's not secret, but you have to have it for verification. So that is Bcrypt. And I'm going to move on to the gold standard Argon 2 in my next video. I hope you liked this one. If you did, please like and subscribe, and I'll see you next time. Thanks, everybody.